Everyone, I'm Simone Paradiso and I'm completing my PhD at University of Milan. And as part of the BeyondPlanck collaboration, I'll talk to you about CMB constraints with this end-to-end error propagation. So let's start from here. You already will be familiar with this slide, with this Gibbs sampling main loop. So we are basically moving, we are basically sampling from not from the joint posterior distribution of in principle billions of parameters by adopting this with this Gibbs sampling scheme. So we are basically moving into orthogonal direction into the parameter space to sample for each sample gain, correlated noise, white noise, bandpass, foregrounds, spectral indices, CMB and foreground amplitudes, and CMB power spectrum. Whenever we talk about cosmological parameter estimate, we focus on these two last steps, which are CMB and foreground amplitude sampling and CMB power spectral estimation. In particular, what is the CMB? What is the CMB amplitude sampling? It's basically solving this equation here, which if you consider only this term is nothing more than a Wiener filter equation. So we are assessing that our map, CMB map in this case, is a linear combination of frequency maps. But whenever we add these two terms, we are basically including also constraint realizations. And what's the result of this sampling, CMB sampling, is a set of maps like this that represents our CMB sky as measured. You can see in the galactic plane the mask imprinting, which is filled with different constraint realization. This is an animation showing some samples from the full dataset provided by BeyondPlanck. And outside the galactic plane, that the CMB has converged to the actual sky realization, but this is not the truth because you cannot, of course, notice maybe, but there is some flickering, and this is due to the fact that within different realization, within different samples, this changing instrumental parameters and also foreground parameters. So we are basically exploring the whole posterior distribution for each CMB pixel. What we get from this set of maps is, of course, an estimate of the CMB temperature power spectrum, which is this black line, to be compared with Planck and Darby map estimates, and to this dashed line, which is the lambda CDM best fit, referring to Planck 2018 best fit. And you can see from the bottom plot that this is basically in good. Our result is in a very good agreement with all these other estimates. Another example of the powerful of this Bayesian end-to-end framework is also the end-to-end error propagation. We use tau as a benchmark because tau is very sensitive to white noise, TOD systematics, and foreground uncertainties. So what I want to show in this plot is how marginalizing over different data sets, for example, blue is just white noise, red and green is marginalization over only TOD uncertainties or foreground uncertainties, and black line is what we quote as the posterior distribution for tau in this case, and therefore the marginalization of all the instrumental uncertainties, how the uncertainties overall changes. And of course it changes, but if you compare the uncertainty to the cosmic variance contribution, you see that the overall uncertainty is dominated by these sources, so TOD, foregrounds, and white noise. So what is the point here is that TOD Gibbs sampling actually includes in a natural way this end-to-end error propagation with both foregrounds and instrumental uncertainties. And just want to highlight also the fact that the most traditional simulation-based method struggle with this accounting for the generalities between different uncertainty sources like foreground and TODs. So what are the cosmological parameter estimates for BeyondPlanck? This one in the red boxes. These estimates come from BeyondPlanck full likelihood alone, and these results come from extending the multiple range up to 2500 using the Planck likelihood code for L greater than 600. And as you can see, we are in very good agreement. We are statistically consistent with Planck 2018 and Darby map results. The only difference, the difference here is the uncertainties. We have larger error bars on parameters, and this comes from the fact that we're using only LFI and Darby map and a limited multiple range. So what is the next major milestone is naturally populating the machinery with state-of-the-art data sets. So the first one, which is obvious, but is clearly HFI, but hopefully we would like to include also proprietary data sets. So here we are with Cosmoglobe for this purpose. And the other goal for CMB cosmologists is, of course, CMB polarization. With the BeyondPlanck analysis, within BeyondPlanck, we were able so far to exploit only the northern hemisphere of CMB polarization data due to a very, very high chi-square excess on full sky. As you can see in this table, when we use a northern and southern hemisphere, we get biases on tau and on our estimates, with, of course, this very low value of chi-square, a very poor fit. We have several issues that were already been addressed at the release conference time in November 2020, and Eric summarized earlier today, which are these coherent stripes, which has been fixed so far at the moment, and noise excess around 1 Hertz that is definitely fixable. But in addition, we have several new effects that are currently under intense investigation, which are ADC nonlinearity correction, 1 Hertz spikes, and improved polarization angle calibration. This very last point is maybe the most important for large-scale CMB estimates, so it's worthwhile giving more in detail a few words about it. So look at this CMB map. This is Stokes-Q CMB polarization map. And you can notice there is this blue structure in the southern hemisphere is like a synchron-like morphology. And this might be related to, is very likely to be related to polarization angles. Why it is? In Planck, in the official Planck LFI analysis, has been included an assessment of the quality of polarization angle measurements. And to do that, it's been used the Crab Nebula as calibrator. These are the results for each LFI detector measurements using this tau A. In the previous BeyondPlanck release in November, these are not corrected for, we did not correct the polarization angles for these measurements here. This would cause a leakage, of asynchronous leakage in the CMB polarization Q maps, and you can see also in this slide a comparison. On the right, still from this Planck paper, there is the DPC polarization angle template using LFI channels, and you can compare this structure in 44 and 30 gigahertz in the southern hemisphere with this structure in the southern hemisphere from BeyondPlanck CMB Q map. We had a preliminary run correcting for these polarization angles. And in this animation, you can see a comparison between what was the polarization maps at the release conference time and what is now, so before and after this correction. And you can see here this blue structure disappearing when using the correct polarization angles. But we are currently preparing, we are currently preparing to include polarization angles as intrinsic free parameter. We want to sample directly within the Bayesian framework for polarization angle using the Crab Nebula as the main calibrator. And we will provide this to the final BeyondPlanck release once this work is completed. So just summarizing what I've shown in my slides, my presentation is that BeyondPlanck has implemented a statistical framework that supports this true end-to-end error propagation for CMB data. We applied and demonstrated this with Planck LFI. We have still some residuals, some large-scale polarization excess in the southern hemisphere, but we address this problem with noise bump, again, stripes, ADC nonlinearity, polarization angles, and so on, everything that has been highlighted during this presentation. And the final BeyondPlanck run is going to happen during the summer, and we aim to have a final release in early fall. We do not make promises about that, but this is what we aim for. We believe this is then the right time to move on from just Planck LFI and apply this framework to many more data sets. The most natural is Planck HFI, but any ongoing and upcoming experiment is welcome, and this might be worthwhile to include for propose some results, some cosmological parameters estimates, which might be competitive with Planck, with what Planck brought to our scientific community. So the future is now Cosmoglobe. Funding, so BeyondPlanck has been funded with European Union grant, and this institution cooperated within this collaboration. So if there is any question, this is the time. Thank you.
Yeah, excellent. Thank you, Simone.